Hello everyone, I'm Jiechen. I'm glad to share with you our recent work on weakly supervised video action segmentation. Our proposed model is NERD with a wide selection of training samples and model evaluation criteria. We address the problem of weakly supervised video action segmentation, which extends the general video object segmentation to additionally consider action labels of the actors. So how can we do pixel-wise segmentation with the video-level actor action labels? We need to synthesize a pool of pseudo annotations to train our segmentation network. For actor label, we utilize the existing 2D-COM GCM model to produce a mask that localizes the actors in each frame. Now the question is, can we infer action mask using 2D-COM GCM? Let's take a look at this interesting example. Can you guess from a single frame what this lovely bird is doing? Watching somewhere? Attracting a mate nearby? Is he sleeping now? Busy eating? As you can see, it's pretty hard to determine the final answer. It all depends on which frame is sampled. Then what if a video clip is provided? It must be eating pretty clear, right? Since an accurate action mask highly depends on a well-trained action classifier that is robust in action recognition, we can hardly infer accurate action mask using 2D-COM GCM because it is based on the 2D-COM action classifier, which is not reliable enough. The spatial temporal dynamics are lost when the action classifier operates on a single frame. Then you may ask, can we infer action mask from a video clip? Absolutely. Motivated by the success of 3D convolutions in action recognition, we extend 2D-COM GCM to 3D-COM GCM for action mask generation. 3D convolutional model like i3D that consumes a video clip as input, then a series of action heat maps are produced from the weighted average of the feature maps in the last convolutional layer. Next, we take the union of the actor and action mask and call it initial mask. The initial mask is mostly a blob, which can hardly serve as a qualified pseudo-annotation with clear boundaries. By the way, pseudo-annotation is referred to as PA hereafter, even if pixel-level ground truth is inaccessible in our setting. We can refine the initial mask to obtain boundary-aware PA that is acceptable for training a segmentation model. How to do that? Well, we propose PA refinement based on SLEEK, which is a low-level superpixel algorithm. At a high level, this can be thought of as treating the initial mask as a superpixel selector. So we impose the initial mask, represented as a sketch in yellow here, onto the superpixel map. It will select the superpixels it has a big overlap with. By this means, the refinement process drags the blob-like initial mask closer to the object boundary. The resultant refined mask is represented by the sketch in orange. We can also quantitatively measure how much the initial mask has been modified using the proposed region integrity index, abbreviated to RII. RII is calculated as a MIOU between the initial and refined masks, and serves as a good indicator as to how close the original mask is to its refined version even before PA refinement. The bigger, the better, which means the original mask already keeps the object shape to some extent. We include this metric in deciding the stop sign for weakly supervised training. With that, it's time to unfold our two-stage framework. The first stage is the initial pseudo-annotation generation. Once the first version of pseudo-annotation pool is ready, it enters the second stage, iterative PA evolution. The quality of PA is inconsistent over the full training set. We devise a select train predict mechanism to facilitate PA evolution. First, a subset of good quality PAs is selected to train a segmentation network. Once the network is well trained, it will make its predictions on a full training set as a new version of PA. The select train predict cycle rolls over again and again until the proposed non-reference metric region integrity criterion is converged. Please refer to our paper and supplementary video for experiments. Thank you.